Here we have a very standard conservation of momentum problem. One of the most common things conservation of momentum is used for is two objects collide with each other and then they fly off in other directions. And we want to know, we know the velocity that they're going to have before the collision. We want to know the velocity that they're going to have after the collision, without, by the way, knowing a thing about how they're actually going to interact with each other, like the nature of those interactions. In this particular case here, just to kind of get us started with something simple, we've got balls that are made of soft putty so that they stick together when they collide, which will make our life a little bit easier. Okay, so the first thing I need to do is identify the system. In this case, the system is just simply the two balls that are colliding with each other. But the important thing being, I have to consider both of them as part of the system. I can't just focus my attention on one. I've got to have both in my viewpoint. And then I need to think about what are the initial and final states here. So these are given pretty explicitly in the question, but I want to make sure that I sketch them out carefully. So I got two objects here. Let's make them different colors so that it's a little bit easier to see. So black and red. It's a head-on collision, it says. So the red one will be going this way, and the black one will be going this way. The mass of the black one will be 0.1 kg. And this one's traveling at 8 meters per second. And for the red one, it has velocity 0.25 kg and velocity 3 meters per second. So there's my initial state. Next, I need my final state. So in this case, the two objects stick together in the collision. So they're going to form one combined ball, which has mass 0.35 kg, the combination of the two individual masses, because it's the merging of the two. Now, one thing that's interesting, and this often happens in these conservation of momentum style problems, I don't necessarily know, without really having a lot of intuition and experience in these problems, is the final ball here going to be going right or is it going to be going left? I'm not too sure. So when that happens, it's totally fine if you don't know the final state. You just need to make a reasonable guess. And it's one of those cases where the math will correct you if you're wrong. So just make a guess, stick with it for the entire problem. And if you get a negative speed, it means that your velocity is in the wrong direction. So I'm just going to arbitrarily assume that this guy goes to the right, knowing in the back of my mind that if I am wrong with this guess, if V is positive, it means I'm right. If V is negative, then it means the ball was actually going to the left. Totally fine, because the answer is going to tell me whether I was right or wrong, which is just as good as being right. You don't have to be right. You just have to either be right or understand when you're wrong and change accordingly. Okay. And next thing is I also need to identify what I'm calling the positive direction. So I'm going to make right as the positive direction for everything. Now I need to write down the momentum in the initial state and the momentum in the final state. So up here, initial momentum. Now remember, the definition of momentum is mass times velocity. So for each momentum that I write down, I'm going to do the mass times the velocity. And then remember that momentum is a vector, so I'll need to sign these. The momentum vector has the same sign as the velocity vector. So if the velocity is going to the right, it'll have a positive momentum. If the velocity is going to the left, it'll have a negative momentum. So that means for the black ball there, we've got 0.1 times 8. I'll write it out longhand just to make sure people can follow. 0.1 times 8. So that represents the black guy. Then the red guy is going to be minus 0.25 kg times 3 meters per second. And that's all just numerical, so I can crunch those numbers there and get an actual number for the initial momentum. So it's going to be 0.8 minus 0.75. So that's going to be positive 0.05 kilogram meters divided by second, which again is the SI unit for momentum. So now we switch to the final picture. For the final picture, this one's going to have a variable in it, but that's totally fine. It's just going to be 0.35 kg times positive V, because V is pointed to the right. And the fact that I made this positive is where my assumption that V is going to the right is going to come into play. The last thing I do is set the initial momentum equal to the final momentum. So the initial momentum is 0.05. The final momentum is 0.35 V. So then I can solve this equation. 0.05 divide 0.35 is V equals positive 0. That's supposed to be a 0.14 meters per second. Okay, and then the fact that it's positive means, yes, my picture is correct here. That is, in fact, the direction that it will go in. And that's all there is to it. By the way, a collision of this type, where the objects stick together, this is referred to as a perfectly inelastic collision, just in case you hear that terminology later. Perfectly inelastic. So if you see that term, that's the same thing as the case we just solved here. That means that the objects stick together. All right, so that's all there is to applying this procedure. I think maybe I'll do another video where I show you another case that's not a perfectly inelastic collision.